In section 2.4, we have some information about the angles of a triangle, classifying triangles, auxiliary lines, and how to prove corollaries. So let's begin with triangles. We have a definition and a symbol for triangles. So a triangle is the union of three line segments that are determined by three non-collinear points. All right, so if we have three collinear points, say these are all on the line, then that's not enough information to determine a triangle. So for example, I could draw this triangle that passes through all three of those points, and I could also draw this triangle and some others as well. So the 3 points, at least one of those has to be non-collinear or not on the same line. The other thing to notice is that the triangle is not like a filled-in shape. So triangles are just these three line segments and the points on those, but this space inside the triangle is not considered to be part of the triangle. So here's an illustration of triangle ABC, and we would use literally a triangle symbol as the is the way to symbolize a triangle. So I would call this triangle ABC. Then there are some other points, the ones sort of inside the triangle. They're not a part of the triangle, but they would be considered to be in the interior of the triangle, just like we talked before about points in the interior of an angle, even though they're not part of an angle. And let's say we had a point out here, point E. Point E is not a part of the triangle, but it is in the exterior of triangle ABC. All triangles can be classified in two ways, so given two names based on their sides and their angles. So you can read through these in the textbook in section 2.4, and you've probably seen these terms before. So scalene triangles, three different sides, sides of different lengths. Isosceles triangles with two equal sides, and equilateral if all three sides are congruent. It seems to be in this textbook that equilateral ones are not considered to be isosceles, so we're going to go with, for isosceles, we're going to go with the definition that exactly two sides are equal, not at least two sides are equal. And then we can also classify triangles based on angles. So they are considered to be acute if all three angles are less than 90 degrees, obtuse if one angle is greater than 90 degrees, so not all three angles, and then right if exactly one angle equals 90 degrees, and equiangular if, you probably know this one, if all three angles are congruent to each other. Now notice here we can figure out the measures of those three equal angles, but in the definition of equiangular, the only thing we're saying is that all three angles are congruent. Okay, so for example, if triangle ABC is equiangular, okay, then don't jump right to assuming the measure of each angle, but all we can say at this point is that angle A is congruent to angle B, and that's congruent to angle C. All right, let's talk about auxiliary lines. So these are helping lines. Okay, that's the definition of auxiliary. And these are usually ones that we draw into a diagram to assist with proofs. So sometimes you need to extend a line that's there, or maybe even draw in a new one that didn't exist in the diagram. So we need to justify why we're allowed to do that. You have to have a reason if you're going to add something to the givens or the assumptions. So here are some of the reasons we can use to justify adding in lines. We know that there is exactly one line through two distinct points. So let's say that let's say we have a rectangle ABCD, and let's say we want to draw in a diagonal from A to C. Okay, well, why are we allowed to do that? Because we know that there is exactly one line through those 2 points A and C. So we're just drawing in that one line that this statement already states exists. We know an angle has exactly one bisector. So if I have a drawing of let's say a triangle ABC, and let's say I want to draw in the bisector of angle B. Well, I can do that because I know that that one exists, and I know that there's not more than one, so I'm drawing it in the exact right spot. And then there's only one line perpendicular to another line at a point on that line. So if I had, let's say a triangle again, ABC, and let's say I have this point P on segment AC, and let's say I want to draw a line that's perpendicular to AC at point P, then I can go ahead and do that. All right, when you draw these lines, we want to make sure that they are always determined, meaning we have just enough information assumed about these lines. So in your textbook, if you refer to page 94, there's a discussion about auxiliary lines that are determined, underdetermined, or overdetermined. So determined means just enough information is assumed. Right? So for instance, if I'm using as justification that it's an angle bisector, okay, then when I draw in that bisector, then it's okay to assume that it bisects that angle. That's, that's okay. We can assume that from that statement. Underdetermined would mean we've drawn something that's possible, but there may be more than one figure that's possible, and we haven't really stated why we're choosing one over the other. And then overdetermined, your textbook states that an auxiliary line is overdetermined if it means that there are some impossible conditions. And then I also want to add to this, it could still be possible, but it isn't necessarily true, so it doesn't have to be true. So whatever we've drawn could be possible, but doesn't have to be. All right, so we want to avoid these second two situations. All right, so let's do some examples. This is exercise 6 from section 2.4, and then I assigned as homework exercise 5, so you would be doing something similar in that exercise. All right, so we need to decide if the auxiliary line is determined, overdetermined, or underdetermined. So let's look at part A, so through vertex B of triangle ABC, so let's draw that. And keep in mind when you draw triangles, like even though this looks acute, I'm not assuming that, so this may very well be an obtuse or a right triangle, or could be scalene, isosceles. I don't know anything about this triangle. All right, now through vertex B, draw line AB. Okay, so through vertex B, draw a line, so you could be thinking about like different possible lines, etc. But we want to draw line AB. Okay, so I know right where that line has to go, so that it's perpendicular to AC. All right, well notice when I do that, that forces a condition on my triangle that doesn't necessarily have to be true. So by drawing that extra line, I'm forcing angle A to be a 90-degree angle. And that isn't something that I want to assume about this triangle. All right, so in this case, this isn't an impossible condition. We could have angle A as a right angle, but it's not absolutely true or not absolutely necessary. We don't know for sure that that's the case. So this would be an example of an auxiliary line that is overdetermined. It's assuming too much or forcing too many conditions into the problem. What about part B? Draw the line that contains A, B, and C. Okay, so think about 3 points, A, B, and C, and draw the line that contains them. Okay, so it's basically saying draw 3 points on a line. Okay, So are there any problems with that? And in this case, no, there are not. So this would be a determined line, so it's just saying draw a line that contains these points A, B, and C. So it's not forcing any conditions on the problem, and it's also not too ambiguous. So if I had these 3 points on this line, there's no other line that I could put through all 3 of these points. So it's just enough information. Alright, so that one's determined. And then part C, draw the line that contains M, the midpoint of segment AB. So let's draw segment AB, and then the midpoint M. Okay, and these are congruent since that's the midpoint. And then draw the line that contains M. Well, which line that contains M? So are we talking about AB? Are we talking about a line like this? Maybe it's perpendicular to AB through M. Could be this one. So in this case, it's possible to draw that. And by drawing a line through M, we're not forcing any extra conditions on segment AB or on M. But notice in this case, there are multiple figures that are possible. So this is an example of an auxiliary line that is undetermined. Okay, meaning it's not possible to draw exactly one line that has these conditions described. All right, let's look at proving a theorem about the angles of triangles. So this is sort of a major one, and this follows from the parallel postulate. So this is interesting because this is one that distinguishes Euclidean geometry from some of the other geometries. So you'll read, or if you haven't already, that in different types of geometries, the sum of the measures of the interior angles of a triangle isn't necessarily 180 degrees. So in other words, we're going to use the parallel postulate as part of our proof for why this theorem is true. Okay, so to start with, we have a specific triangle, ABC, and then to assist in the proof, we're going to draw an auxiliary line, ED. And then often when we draw these, we will redraw the diagram so that way we can see the givens without that line drawn in, and then we can see what we've added to the diagram, and it just makes it a little bit more clear. So we want to draw, and sometimes we'll say construct, or you can say draw or create. So construct line ED through C parallel to AB. Okay, well, why are we allowed to do that? So this is by the parallel postulate, and this is the one that says that through a point not on a line, so through C that's not on AB, there's exactly one line parallel to that other line AB. Okay, so I'm drawing the one line, ED, that's parallel to AB and runs through C. All right, so now this creates some additional angles. So angle 2 here was part of the triangle, but angles 1 and 3 are now created by that auxiliary line. And we can use all of those angles in our proof. So let's label these angles A and B. I'm going to label these as 4 and 5. All right, and then we want to prove that the measure of angles 2, 4, and 5 add up to 180 degrees. So that's our goal. All right, well, we know that, and then again, I'll just do sort of an outline here, and you could fill in more of the details yourself, but we know that the measures of angles 1, 2, and 3 add up to 180 degrees. Okay, and there's a few steps before that, but basically those 3 angles are on line ED, so therefore they add up to 100. They're supplementary, or they add up to 180 degrees. And then from there, let's try to figure out how that relates to 4 and 5. All Right, so one of the things that's convenient now, we know that ED and AB are parallel, so we could bring in any facts we have about parallel lines, so start thinking about corresponding angles, alternate interior, consecutive interior, alternate exterior, etc. All right, so one of the ones, the pairs that are related would be 1 and 4. Okay, so think of AC as the transversal. Okay, and through these parallel lines. Okay, well then 1 and 4 would be alternate interior angles. So then we would know that angle 1 is congruent to angle 4, and therefore their measures are equal. And I don't know if we talked about this arrow before, but this means implies, or therefore, or like thus. So since the angles are congruent, then their measures are equal. Similarly, for angles 3 and 5, okay, if we think of CD as the transversal, then 3 and 5 are also alternate interior. So we know 3 and 5 are congruent, and therefore their measures are equal. And now we can use some substitution in this previous equation. So let's replace 1 with 4 and 3 with 5. And then we've proved what we need to. So those are the 3 angles in the triangle. So 2, 4, and 5 add up to 180 degrees. All right, so this is a major one. And then based on this theorem, there are some other smaller facts that we know and can prove. So we consider these to be corollaries. Now some textbooks won't make a distinction here. They might just call these theorems. But a lot of times a corollary, this word is used to emphasize that this fact is based on a previous theorem. So you'll usually see these that they'll follow consecutively right after a previous theorem. And so in this case, corollary 2.4.2 would be a fact that's based on the theorem right before it, which was this one that in a triangle, the sum of the measures of the interior angles is 180 degrees. All right, so the fact that we're trying to prove now is that each angle of an equilateral or equiangular triangle measures 60 degrees. So you probably know this already. You can probably even see why it's true. So let's run through the proof. It's fairly short. All right, so let's suppose that ABC is an equiangular triangle. So suppose ABC, triangle ABC is equiangular. All right, so what does that mean? Well, by definition, that means that angle A, so then angle A is congruent to angle B, and that's also congruent to angle C. So all 3 angles are congruent. All right, we know by the previous theorem, so by theorem 2.4.1, we know that the measures of these angles add up to 180 degrees. All right, and maybe before that, we should have said then that the measures of these 3 angles are equal, so I can insert that now as well. Okay, that's the definition of congruence. So maybe I just want to say we know, and you could say by definition of congruence, that measure of angle A equals measure of angle B equals the measure of angle C. And now I can use substitution a couple times. So if I substitute the measure of angle A in place of B and C, then I would get the equation measure of angle A plus measure of angle A plus measure of angle A equals 180. and then by substitution I can add these three and get 3 measure of angle A is 180, and then that would mean that the measure of angle A is 60 degrees. All right, and then I can go back and substitute that into this equation where all 3 angles have equal measures, and that would prove that the measure of angle B equals 60 degrees, and also that C is 60 degrees. All right, so you can probably see why this is a corollary, why it's based on that previous theorem, because once we have this fact that they add up to 180 degrees, then it's just some elementary substitution in algebra, a really short proof to show that all 3 angles have to each measure 60 degrees. All right, and then finally let's wrap up just by talking about exterior angles to a triangle. So we have the interior ones, right, are just the 3 inside of the triangle. Exterior ones are of course on the outside, and then to draw one of these you would extend one of the sides of a triangle. All right, so here we've extended side BC, and then this exterior angle is formed. All right, so in other words, you can't just, like I can't just start at B or like at A and draw like this line to make exterior angles, because I haven't extended one of the sides of the triangle. But if I take AB and just keep extending it, okay, then this is an exterior angle. And I could also extend AC and come up with this exterior angle. All right, and so basically in figure 226 part B here, this shows you all of the possible exterior angles. So there are 6 that are possible. And notice then that we've got some vertical angles, so they come in pairs, so at each of the 2 exterior angles at a vertex of the triangle, those would be congruent to each other. All right, I've left some of the facts about exterior angles for you as exercises, but there's a corollary that talks about the exterior angles. And it says that the measure of an exterior angle to a triangle equals the sum of the measures of the 2 non-adjacent interior angles. All right, so if we looked at this exterior angle, then we have 3 interior angles, and we want to look at the 2 that are non-adjacent. So this one would be adjacent. Okay, it's right next to that exterior angle, so we want to look at the 2 A and B that are non-adjacent, and then that corollary says that the measure of angle A plus the measure of angle B equals the measure of angle C. All right, so I've left that for you to prove, but notice that it is a corollary, so to prove it you should look back at the theorem that precedes it, which is the one about the 3 interior angles adding up to 180 degrees. So that's going to be a key step in the proof.